In this video, we're going to talk about curve sketching non-polynomials. How about the first one we look at be f of x equals 1 over x. Now, from pre-calculus, we should know what this one looks like. It goes like this. It goes like that. But let's use calculus this time. So, what you want to do is get the two horizontal asymptotes. You take the limit as x goes to positive infinity of 1 over x. This is going to be 0, but since the numerator is positive and the denominator is positive, when x is really large, it'll be a little bit more than 0. The limit as x goes to negative infinity, again, you're going to have 1 over infinity, so it's going to be 0. But the top is always positive, it's 1, and the bottom is going to be negative, very negative, and positive over negative is negative. So when x is close to negative infinity, it'll get close to 0, but always below. Now, let us look at the vertical asymptotes. They occur when the denominator is 0, but the numerator is not. So, when x is 0, the denominator is 0, but the numerator is always 1. So now, we need to look at the limit as x goes to 0 from a little bit below and from a little bit above. Now remember, a vertical asymptote, the graph gets close to that vertical line. 1 over x. Now, 1 over a really, really small number is going to be infinity. But the question is plus or minus infinity. Well, the numerator is always positive. It's 1. And the denominator, when x is close to 0, is going to be negative because it's going to be less than 0. It's going to be negative. So that's going to give us positive over negative, which is negative. When x is a little bit more than 0, 1 divided by really, really close to 0, again, is either plus or minus infinity. The numerator is always positive, it's 1. And the denominator is a little bit more than 0. That makes it positive. Positive over positive is positive. Okay, now let us take the derivative. F of x is equal to 1 over x, which is x to the negative 1. I wrote it that way in preparation of taking the derivative. You bring down the power, make the new power 1 less. This is negative 1 over x squared. And this is always negative. This is always negative. Okay, let us take the second derivative. Bring down the power, you get 2x to the negative 3, which is 2 over x cubed. Now, let us make up our famous table over here. Negative infinity to 0, because 0 is the only point that came up. That is, the first derivative is never 0, but it's undefined when x is 0. The second derivative is never 0, but it's undefined when x is 0. So the only critical value or possible point of inflection is x equals 0. And we'll look at f prime, and we will look at f double prime. As I said, that's always negative. Okay, so it's always decreasing. And 2 over x cubed, well, the numerator is always positive, And if you cube a negative number, you get a negative. And if you cube a positive number, you get positive. These numbers are all negative. Those numbers are all positive. So it's negative, and then it becomes positive. From negative infinity to 0 is concave down, and from 0 to infinity, it is concave up. Now, let us draw this stuff. So, it's hard to draw the vertical asymptote because it's the y-axis, but there it is. That's the vertical asymptote. Now, when x gets really, really large, positively large, the graph is going to be just above 0. That's way out here. And when x is negative, going to negative infinity, it's going to be a little bit below 0. Okay? A little bit below 0. And what about on both sides of the vertical asymptote? If you're a little bit to the left of 0, the function is going to be negative infinity. That's a little bit less than 0. We're going to be down at negative infinity. And when x is a little bit more than 0, you're heading towards positive infinity. A little bit more than 0, you're way up there. Okay. Now, it's always decreasing. It's always decreasing. And it's not going to cross that vertical asymptote. It's always decreasing. And the concavity, if I can get there, the concavity, well, first it's negative. Well, that's going to be like that. Oops. And then it's going to be concave up, and that's going to be like that. It's exactly what we expected to get. So that's the good practice one, in my opinion. One where you know what you're supposed to get. Now, suppose we have this graph, or this function that we want to graph. This over, say, x squared minus 25. First thing is maybe find the horizontal asymptotes. What's the limit as x goes to infinity? Well, the degrees, they happen to both be polynomials, and the degrees are the same, so you're just going to get 1 over 1 or 1. And this function doesn't care whether, at least when x is very large, whether you plug in plus or negative infinity, because it's being squared. Oops, I should have the limit of f of x. And it's also going to be 1. Okay, so we have that. Now, what about the vertical asymptotes? You have vertical asymptotes at x values that make the denominator 0. Well, when is x squared minus 25 0? Well, when you subtract two quantities and you get 0, those two quantities have to equal one another. So what number or numbers, if any, when you square them, give you 25? And the answer is plus or minus 5. So this tells me that I have to look at the limit as x goes to 5 from above of f of x, because 5 is a vertical asymptote, and they come in pairs. I have to look at what happens when x is a little bit less than 5. And there's a second vertical asymptote at negative 5. So we have to look at negative 5 from the left. Let me be consistent. From the right and from the left. Okay, so you have 5 squared minus 25 over, minus 2 on the top. And on the bottom, if we factor it, we get the difference of squares. That's x plus 5, x minus 5. Now, when you plug in more than 5 or less than 5 for either of these, you're going to get around 25 minus 2. The numerator is going to be positive in both of them. Now, what about the denominator? The denominator has two factors. Well, if you're anywhere near 5, a little more or a little less, and then you add 5, you're going to be near 10. Maybe a little more than 10, a little less than 10. But it's positive. This is the one that gives you 0. If you're a little bit more than 5, if you have more than $5 in your pocket, and you take away 5, you'll have something left. A little bit more than 0. Okay, if the denominator is approaching 0, you're gonna get infinity. We are gonna get positive infinity. Now, what happens on the other one? What happens if x is a little bit less than 5? Well, if you have less than 5, if you have less than $5 in the bank and somehow they allowed you to take out $5, you owe them. You're negative. It's going to be 0 negative. And positive divided by positive times negative is negative infinity. Okay, now let's do the same thing all over again, but let's do it at the other vertical asymptote, which happens to be negative 5. And always at vertical asymptotes, you're gonna get infinity. You're always gonna be infinity. Plus or minus infinity. We need to decide. If you're anywhere near negative 5 and you square it, it's going to be around 25. A little bit less than 25, a little bit more than 25. But when you take away 2, the numerator is going to be positive. Okay? Now, if you're anywhere near negative 5, a little bit more, a little bit less, and you take away 5, you're going to be even more negative. So that second factor in the bottom will be negative. This is the one that gives you trouble. If you have a little bit more than negative 5, so here's 0, here's negative 5. Now, at negative 5, if you add 5, you get to 0. That's key. If you're a little bit more than negative 5 and you add 5, you will become positive. This overall sign, positive over positive times negative, is negative. Okay, but now, what if you're a little bit less than negative 5? What if you're over here and then you add 5? You didn't quite make it positive. So it too will be negative in the bottom. That's going to give you positive infinity. Okay, now we have that, which is really good. Let us look at the derivatives so we can make up our famous chart. Maybe I can get that in the middle here. So f prime of x is the quotient rule. Sorry, it's the quotient. So guess what formula I'm going to use? I'm going to use the quotient rule. It's the derivative of the top, which is 2x, times the bottom, minus the top, x squared minus 2, times the derivative of the bottom, which is also 2x, all over the bottom squared. Well, in the numerator, I can factor out a 2x, and then I have x squared minus 25 minus x squared minus 2. And this is all over, the denominator squared. x squared minus 25 squared. And there's the 2x in front. Well, x squared minus x squared cancels to 0. And negative 25 minus a negative 2 is negative 23. So the derivative is negative 48, negative 46x. Oh, okay, I knew that didn't sound right. Quotient rules don't work out that nicely. Over the bottom square. Oops. Over the bottom squared. X squared minus 25 squared. So yeah, we get negative 46x in the numerator, but we get this mess in the denominator. Now, when does this equal 0? This equals 0 when x is 0. And it's undefined at plus or minus 5, but we already know that. We have our vertical asymptotes there. Okay, and for the record, what does y equal when x is 0? Well, that piece will be 0, so the numerator will be 0 minus 2 or negative 2, and 0 squared is 0, minus 25 is negative 25, so you'll end up with positive 2 over 25. Okay, that's the point where the derivative is 0. So let us try to graph what we have. We know that at 5, we have a vertical asymptote. That's 5. We know at negative 5, we also have a vertical asymptote. X and Y. And we know that the limit, the horizontal asymptotes are 1. Now, let's think if it's going to be more than 1 or less than 1. Now, let me write it here. So far, it's a tie. So now we take away 2 and we take away 25. Which is going to be bigger? So x is really, really large. And here we only take away 2, and here we take away 25. The numerator is bigger. The numerator is bigger. So that's going to make it a little bit more than 1. And whether we plug in negative infinity or positive infinity, this part's going to be the same. It's going to be close. It's going to be 1. So, you know, you're going to have 100,000 minus 2 over 100,000 minus 25. And this is going to be greater than 1. Just a little bit greater than 1. The reason is, in the numerator, I mean, think about it. Who's going to have more money in the bank? You both start off, you and I start off with $100,000. You take out $2, I take out $5. You're going to have more money than me. The numerator is larger than the denominator, but they're about the same. It's going to be more than 1. Whenever the numerator is larger than the denominator, you are more than 1. Okay, you have to be able to think like that. You can think like that, you get good at these problems. So we know that when y is 1, at the very extreme values, let's call that 1. it's going to be a little bit more. Okay, got it. Understand completely. Now, what happens at the vertical asymptotes? If I'm a little bit less than 5, I go to negative infinity. Well, here's a little bit less than 5, and as I said, I go down to negative infinity. If I'm a little bit more than 5, like up here, I go to positive infinity. Okay? A little bit more than 5. Let me make this a little bit taller. I go to positive infinity. Let us look at the other vertical asymptote, the one at negative 5. From a little bit more than negative 5, which is about here, I equal negative infinity. A little bit more than negative 5, I come way down there. What if I'm a little bit less than negative 5? From a little bit less than negative 5, I'm at positive infinity. This here is a little bit less than negative 5, and I am way up there. Okay. The function goes like this. It goes like this. And whenever the 2 points are down here, it's going to be a U shape. It's going to go up, and then it's going to come down. So the question is, where's it going to max out? And maybe now that should have motivated us to look at the first derivative. It equals 0 when x is 2 over 25. And that's less than 1. So when x is 0, call that 2 over 25. Should be a little bit lower, but I already drew part of it. There is your graph. Okay. There's really no need to take the second derivative to find out if the concavity goes like that. It will. These rational functions will go like this. They'll never go like that. It just won't happen. And there's that graph. Okay. Let us try another problem. Just keep hacking these out. Suppose you come to learn that f of x is equal to x squared minus 2x plus 4 over, say, x minus 2. So how about horizontal asymptotes? Well, as x goes to infinity or negative infinity, you're gonna get infinity. The numerator is larger. So in this type of problem, you really should do the long division. X goes into x squared x times. Multiply that by x, get x squared minus 2x, and you subtract. So that's going to give you 0, and then you bring down the 4. So this becomes this. Now, as x, so we want the limit of x plus 4 over x minus 2. Now, this, if x is going to 0, if x is going to infinity, it's going to 0. So the limit is x. Now, let's just decide if it's more than x or less than x. The 4 is positive, and if x is really large, x minus 2 is positive. So it's going to be a little bit more than y equal x. Now, what happens if x goes to negative infinity? Well, it's still this function. And maybe in this one, I'll replace x with negative x. So I can talk about the limit as x goes to positive infinity. So it's negative x or minus 4 over x plus 2. I factored out, so this will become negative x minus 2, and I factored out the negative sign, and I put it as subtraction. Now the thing is, that's going to go to 0. So we're going to go to negative x. Now, if x is going to infinity, this will be positive, but we're taking it away. So we have negative x, and then we're taking away some more. It's going to be a little bit less than negative x. Okay, so we have the vertical asymptotes. Whenever the degree of the bottom is smaller than or equal to the degree in the top, I think you should do long division. In fact, in the last problem, right here, if we did the long division, how many times does x squared minus 25 go into x squared minus 2? One time. And you have x squared minus 25. If you subtract, you get 23. So it is going to be, I'm going to go up, it's going to be 1 plus 23 over x squared minus 25. Well, I guess when they're the same, you don't have to do the division. The degrees are the same. Because when x goes to plus or minus infinity, that's going to go to 0. So the whole fraction will go to 1. And this will always be a little bit more than 0, so it's 1 plus. Okay. So we did the horizontal asymptotes. Now let us look at the vertical asymptotes. And just for completeness, that division was part of the horizontal asymptotes. So now we do the vertical asymptotes. Well, a good candidate will be x equal 2. But we need to make sure it doesn't make the denominator 0. I meant to say the numerator 0. 2 squared is 4, minus 2 times 2 is 4, so that's 0. And when you add 4, I don't really care what you get, but you don't get 0. A vertical asymptote is an x value that makes the denominator 0, but not the top. So fortunately, we only have one of them. So we need to do this limit game for just one x value, 2. And it's always, the limit is x goes to 2 plus in this case, and the limit as x goes to 2 minus of x squared minus 4x plus 4 over x minus 2, and x squared minus 4x plus 4 over x minus 2. And I lied about us not wanting to know the exact answer when we plug 2 in. The exact answer is 4, which is positive. Okay. So we're going to get infinity. The numerator is positive. It's positive 4. Let me write this a little bit smaller. So the numerator is positive. And the denominator, well, if you little bit more than 2 and you take away 2, you'll be positive. So the overall answer is positive infinity. We know it's going to be infinity. If you're anywhere near 2, the numerator is going to be near 4, which is positive. Well, only when you're at x minus 2 do you care about more than or less than. If you're a little bit less than 2 and you take away 2, you're going to be negative. So this is negative infinity. So the vertical asymptotes are over. And it's always good to know the y-intercept. What is f for 0? Well, if you plug in 0 in the numerator, you're just going to get 4. If you plug in 0 in the denominator, you're just going to get negative 2. So f for 0 is negative 2. That is, we're going to cross 0, negative 2. That's the y-intercept. And we have a vertical asymptote at 2. So in terms of graphing this, I have 2 in my mind. In terms of graphing this, we know that at 2, we have a vertical asymptote. So there it is. And in terms of the horizontal asymptote, when x is approaching positive infinity, I'm going to be getting closer and closer to the line y equal x. Well, here is the line y equal x. Remember, I'm going to be a little bit more than that. So I'm there. The other end, we're getting closer to, as x goes to negative infinity, we're getting closer to negative x. But I'll be a little bit below that. Y is equal to negative x goes like this. And I'm not going to draw it past the x equals 0 because this is happening when x is really negative. So I'm going to be a little bit below it. Okay. Now, what happens when I'm a little bit more than 2? Vertical asymptotes. From a little bit more than 2, I'm going to positive infinity. A little bit less than 2, negative infinity. So from a little bit more than 2, let me draw this just a little higher. I'm going to be positive infinity. If I'm a little bit less than 2, I'm going to be here. And I'm going to cross the y-axis at negative 2. Okay, the graph is going to look like that. Now, this one's going to be a little bit harder to pull off. Maybe if I make this lower, I'll have better success. So, it has to go like that. But I know I didn't do a great job, but it's supposed to be concave down. Okay, and there's the graph. There's the graph. Let us do one more function. This one will not be a rational function. Suppose f of x is equal to x over the square root of x squared plus 2. Now, this is approximately equal to x over just the square root of x squared. But that equals to x over the absolute value of x, and that's going to be plus or minus 1. If x is positive, you get x over x, which is 1, and if x is negative, you get x over negative x, which is negative 1. And this is going to be true if x is large. positive or negative. Because even if this wasn't always positive, when x is really large and you square it, positive and negative, and you square it, you're going to get a large number. Adding the 2 becomes less and less meaningful. So actually, let us erase that and let's do it more formally. What is the limit as x goes to infinity of x over the square root of x squared plus 2? Now, this 2 becomes less and less meaningful as x gets larger and larger. But it is getting larger and larger. So this just becomes x over the square root of x squared. But as long as x is positive, the square root of x squared is x. And basically you have the limit as x is going to infinity of 1. X will never reach infinity. So you'll have 20 billion over 20 billion. You'll never have infinity over infinity. So the limit is 1. Now, what happens as x goes to negative infinity of this? Well, this is complicated. So let's look at the limit as x goes to positive infinity. And I'll replace x with negative x. Now, when I replace the x in the bottom with negative x, since I'm squaring it, it didn't matter. This is now the limit as x goes to infinity of negative x over the square root of x squared plus 2. Now, constants like negative 1 can come out in front of the limit. You have the limit as x goes to infinity of x over the square root of x squared plus 2. But we just did that limit. And we got 1. So this limit is going to be negative 1 times 1, which is negative 1. Okay. So what we do know, 1 and negative 1. When x is really large, let's label this. When x is really large, the graph is going to be getting closer and closer to 1. And when it's going to be negatively large, it's going here. 1, negative 1. Well, is it going to be more than 1 or less than 1, more than negative 1, less than negative 1? Let us look at that. Well, this denominator, the square root of it, will always be more than x. Okay? It will always be more than x. Because if you only had x squared, the square root will be x. But you have 2 more. So it's always going to be bigger than x. And numerator is just x. If the denominator is bigger than the numerator, you are going to be less than 1. That's why I'm putting that dot just below 1. Now, let us look at this one. Now, once again, this is the same limit as before. So this is going to be a little bit less than 1. It'll be like 0.999. Okay? And when you multiply it by negative 1, it's going to become negative 0.999. That's actually bigger than negative 1. We're not quite getting to negative 1. We're going to be just above it. Now, this problem has no vertical asymptotes because the only way the square root of something is 0 is if the something is 0. But that's always at least 2. There are 3 types of numbers. And when you square them, you either get positive or 0. So x squared is either positive or 0. And if you add 2 If you add 2 to a positive, you're positive. If you add 2 to a positive, you're positive. And if you add 2 to 0, you're positive. This is always positive. It is never, ever 0. So we have no vertical asymptotes. And I always suggest we find the y-intercept if x is 0. If x is 0, we get 0 over the square root of 0 squared plus 2, which is 0 over the square root of 2, which is 0. So we know that this function has 0 right here. It crosses at 0. And they're always nice curves. The curve is just going to go like this. This completes the section on curve sketching non-polynomials. Do lots of these. They'll become easier and easier.